Okay, this week we discuss about the thermal properties of materials. That means when the temperature changes, what will happen to the material. So we are discussing three things here. How the heat is transferring, heat flux. And also the next thing is how the temperature increases because or decreases because of the heat. And the other part is the thermal stress expansion, or the materials will expand with the temperature and contract with and when we increase increase the temperature, material will most of the material will expand, and when we decrease the temperature, the material will contract. But it's different in water. When we cool, when the water becomes ice, that will expand. So cooling, upon cooling, ice water is expanding, but most of the materials are expanding with the temperature, high temperature, and when we decrease, it will compress. So here, this is the summary that you have done. So if you consider the heat capacity is the energy required to increase a mole of material by unit temperature, and this energy is stored as atomic vibrations. Thermal expansion is the size of material changes with the change in the temperature. So polymers have a largest coefficient of thermal expansion, and thermal conductivity is the ability of materials to transport heat, and metals have the largest value, and thermal shock resistance is the ability of materials to be rapidly cooled or not fracture. So these things you have discussed in your lecture, am I right? Okay. So the heat capacity. We have two definitions here, heat capacity and the specific heat. The difference between these two, if you look at these ones, one is the energy required to produce a unit rise in the temperature for 1 mole. But the next one is the same thing for 1 kilogram. So if you look at these two units, one is joules per moles per Kelvin, the other one is joules per kilograms per Kelvin. So that's the difference between these two is one is for a 1 mole and the other one is for a 1 kilogram. Are we okay? Any question? No questions? We may using these equations, okay? In solving questions. Next, we need to know thermal conductivity. Thermal conductivity, when relevant to thermal conductivity, it is the ability of materials to transport heat. So we use this Fourier's law for doing calculations for thermal conductivity questions. So heat flux, that means the joules, the energy per square meter per second, how much of heat energy is transferring per unit area per unit time per second, that we call the heat flux. And you can find the heat flux if you know the thermal conductivity of the material and the change in the temperature divided by the distance. So if you measure the distance in X, and if you consider the change in the temperature T final, or else this side is maybe T2 and this side is T1, so that change in the temperature divided by the change in the, or else this distance traveled, and times K will be your simple Q. This negative sign is because your simple Q is always a positive number. Change in the temperature, heat is transferring from high temperature to low temperature. So that's why it's final minus the initial, always a negative value. To get rid of the negative value, we have a negative sign in front of this equation. So your Q is always, simple Q is always a positive value. Are we good? And simple Q is per meter squared per second. If you want to find the total heat energy transferred, that means your capital Q, you need to times this simple Q by the area and the time in seconds, so that you can find the total energy in joules. Does that make sense? Any question? And there is another unit that we use, that is W watts. That means joules per second. We can, that's we call the watt. So in some cases, this units will given as, sorry, not that one. This unit will give us watts per meter squared. In some questions, you will find that because watts is equals to joules per second. The next one is the thermal expansion. So materials, as I have mentioned at the beginning, materials will expand with the high temp when we increase the temperature, and material will decrease, contract when we decrease the temperature. So that equation is this one. So final, or the change in the length divided by the original length is equals to thermal expansion coefficient linear value times the delta T, change in the temperature. So sometimes if you consider the change in the area divided by the area, that will be the thermal expansion area, thermal expansion coefficient times the delta T. If you consider the change in the volume, change in the volume divided by the original volume, that will be volume expansion coefficient times the delta T. So these three, do you understand the difference between these three? In today's, all the calculations are with this one, so you are not going to talk about these ones, but the area means we are looking at the area, and volume means we are looking at the volume. And the other thing, are you familiar with this delta LOL note? Have you heard of this one anywhere else? Have we discussed that anywhere else? Are you familiar with this? Are you familiar with this one? What do we call this? That's the strain. So you discussed that in the mechanical properties. What is the relationship between stress and strain that you have discussed? Stress is equals to strain times the Young's modulus. Am I right? So if you make the strain the subject in this equation, that will be the stress over the Young's modulus. So you can substitute that one here. If you want to, you can substitute this one here, and you can find an equation for stress. So stress over Young's modulus is equals to expansion coefficient times the delta T. So you can make the stress the subject. So stress is equals to E times alpha times delta T. So this stress is due to the temperature changes. So thermal stress, we call this the thermal stress. Is that make sense? So when you consider the thermal stress, what will happen? So next slide is thermal stress. So thermal stress, you can use this equation. That's what we have we got before. So for example, if you have two fixed supports, have you done fundamentals of mechanics? So you know what is fixed supports, okay? So when you increase the temperature, what will happen to this beam here? That will expand. So, but you have two fixed supports at the two ends. The material is trying to expand, but the supports are not letting it to expand. So what is happening? So supports are pushing, so that there is a compressive forces. Do you agree with me? So material is undergo compression. Agree? Similarly, when you have the same thing, but if you decrease the temperature, what will happen? When you decrease the temperature, material is trying to shrink, but the supports are pulling it. So what kind of a stress that it will undergo? Will undergo a tensile stress. Am I right? So when the temperature decreases, if you have fixed supports, if we are not allowing the material to expand, that will undergo tensile stresses. And if we increase the temperature, and if the material can't expand, then it will undergo compressive forces. So you can, upon heating, material will undergo compressive stresses. Upon cooling, the material will undergo tensile stresses. Are we good? Any question? Okay, so we are going to use this equation as well in our questions. Okay, now let's start with the first question. I think you don't see the question. So So the question here, calculate the heat flux through a sheet of steel, which is 10 millimeter thick. 10 millimeter thick. If the temperature at the two faces are 300 and 100, assume steady state heat flow. So what they say, they are saying we have a 10 millimeter thick steel, and one side is 300 degrees Celsius, the other side is 100 degrees Celsius. They are asking you to find the heat flux through the sheet. So heat flux, that means simple Q, which is equals to this. Am I right? Is this right? That equation we discussed at the very beginning. So we need to know this K value for steel, which is this one. So K is known 51.9 watts per meter squared. Watts per meter, sorry. And then we have delta T, you know, which is 200 degrees Celsius, and delta X is 0.01 meters. So you can put these values and you can find me simple Q. So can you please find me simple Q? Meters per Kelvin, okay. And your Q is in watts per meter squared, or else you can say joules per second per meter squared, both the same. So can you find me Q, please? Heat flux. Nine, yes. What's the meters per Kelvin? What's the meters per Kelvins? Right. So what do you get for Q? So this negative sign will cancel out because, like, you know, you have a negative here. When you consider the temperature, that will be 100 minus 300. It is negative 200. So negative will cancel out and you get a positive value. Your Q is always a positive. So it's, what do we get for simple Q? 1.045. 10 to the 6. So do we all get this? Are we all good? It can be watts per meter squared or else joules per second per meter squared. So what? Any, it's okay because this is equals to this. When we say temperature in degrees, doesn't matter if it's in Celsius. It doesn't matter as long as it's a difference. So if you make it to Kelvin, you have to add 273 for both 100. It will cancel out. So when you consider change in the temperature, it doesn't matter whether it's the same for Kelvin and degrees. So it doesn't matter. Are we good? And then in the next part, they are asking you to find, so this is what we did. We found the heat flux, and then they are asking us to find the heat loss per hour for the area of this. So simple Q is per per area, per square meter per second, isn't it? So joules per square meter per second. Now you need to find the total heat energy. So that will be, if you times this Q by the area and the time, that will give you the capital Q. So can you please find me the capital Q, which is the total heat loss that they're asking us to do for an hour. So hour means you need to put this in seconds because you have in seconds here. So that means 60 times 60 seconds. An area is given to us, which is 0.25 meters squared. This one we found, which is 1.038 times 10 to the 6. Is that right? So what do we get? Yes. 9.342 times 10 to the 8 joules. Do we all get that? Okay, now in the next part of the same question, they are saying, what will be the heat loss? Again, they're asking you to find the Q for an hour. If soda lime glass was used as steel, so wow, your K is different this time. Thermal, am I right? Thermal conductivity will be different. We can refer the table, but I will give you the number. So K for soda lime glass is 1.7. So use this and find the Q first and then find the capital Q. So Q is negative K times delta T over delta X. So delta T is the same, which is 200 degrees Celsius, and delta X will be the same, 10 millimeters, which is 0.01 meters. And your only K will be different. So find me the simple Q. And then they're asking you to find the capital Q, which is Q times area times the T. So again, nothing will be different. Time is 1 hour. And this one is 0.25 meters squared. So can you find me these two, please? It was 9.342 times 10 to the 8 joules. Did you get it or not? Yeah. The area the same? Area is the same, yes, 0.25 meters. So simple Q will be 34,000. Yes, that's right. And then 3.06 times 10 to the power. Do we all get this? So they are not hard, they are easy. Can you look at this? Okay, next part of the same question. Calculate the heat loss. Now, your steel, we use the steel, but the thickness is increased to 20. So your delta X is now 0.02 meters. The rest will remain the same. So you need to find the capital Q here for 1 hour. So you need to again find the simple Q, which is we can use this equation to find that one. So if you can remember, this was 51.9, is that right? Yes. And temperature doesn't change in the temperature. This is changing to 0.02 meters now. So you can find this, and then you need to find the Q, capital Q, that will be simple Q times A, area times the time. So area and the time doesn't change. But do we get for the, so the heat flux will be less because if it has to travel longer, so it's less. So that will be half, yes, half, isn't it? So that will be 5.19. It's 5.19 times 10 to the 5. Do we all get this? And capital Q is what? What do we get? Is this right? So that's regarding the flux, heat transfer. Yeah. So heat transfer, any question? Do you have any question regarding heat transfer? But you may have 467. Yes, so that's the same thing, isn't it? Okay, next question. So this is regarding the thermal stress. So thermal stress, I already explained you. The end of a cylindrical rod, 6.4 millimeter diameter and 250 millimeter long, are mounted between a rigid support. So rigid support is something like this. They are saying temperature is changing from, so there is no stress at the room temperature. Room temperature, it's in the normal size. And it is cooling to negative 40 degrees Celsius at a maximum thermally induced tensile stress of. This is possible. This is the possible value. So maximum stress that the supports can take is 125 megapascals. Of which of the following metals or alloys may the rod be fabricated? So we have few options here. So we can either make it with aluminium, copper, brass, steel, or tungsten. And they're asking which ones are okay, which ones are not okay. So if you consider the stress, is this one undergoing a compressive stress or a tensile stress? Cooling, we are cooling, so it is going to shrink, but the supports are pulling them up. Tensile stress. So this is undergoing tensile. So that's tensile stress we can calculate. How we calculate it? Thermal stress. We can calculate it this times the change in the temperature. Do you agree with this? We already discussed this equation, how it came. So here, this is not changing for any material. This will be, how much will be the change in the temperature? It's negative 60, or else you can, yeah, you can make it to 60, and you need to understand this is tensile, okay? Cooling tensile, otherwise you need to put everything with the signs negative. So negative means, so you can, then you have to think and do it, okay? So here, so this will be 60 degrees Celsius. But these two are material properties. So depending on which material you use, this will be different. So what should be if that material is okay? So for example, let's say aluminium. When you find the aluminium, the stress induced in aluminium due to this temperature change, if this one, how you recommend? Aluminium is okay or not? What should happen? the stress induced in the aluminum should be less than this 125 megapascals. Am I right? Yeah. Because this is the maximum allowed by the supports. But if your material is undergoing more than that, that will break, isn't it? So as long as the material, the stress induced in the material, thermal stress induced in the material is less than 125, we can recommend that particular material.
So the more the young module, please, the better like chance is being less than 125.
It depends on the Young's modulus and also for the thermal, yes. For the thermal, yes. Young's modulus and also for the alpha.
Yeah.
Okay, so yeah, I'll give you these numbers. Okay, so let's do with the aluminium. So for aluminium, E is 69.10 to the 3 megapascals. And this one, alpha, is 23.6 times 10 to the negative 6 per degree Celsius. So just use these two and find me stress for aluminium. So stress for aluminium is what?
$577.
97. Am I right? 97.7.
0.9 or 69 times 10 to the power
So I have it as 69. Should it be so don't you get this? Your answer, I just kept this as megapascals because our answer also will be in megapascals.
Yeah,
What's that?
wait, is it to the power of 3 or negative 3?
Sorry, power of 3. Yes, power of 3, sorry. What do we get? Do we get 97.7 or is it something else? Okay, so what can you say about aluminium? Is aluminium okay or not?
Yeah, it is.
Aluminium is okay, right? So we can say aluminium is okay. So I want you to check for the copper, brass, steel, and tungsten in the same way. You use the same equation. Only thing is your E and alpha will be different. I'm going to write you the E and the alphas here. So you have to do it and tell me which ones are okay and which ones are not okay. So for copper, E will be 110 times 10 to the 3 megapascals, and alpha will be 17 times negative 10 to the negative 6 per degree Celsius. That for copper. And for brass, E will be 97 times 10 to the 3 megapascals, and alpha will be 20 times 10 to the negative 6 per degree Celsius. And for steel, E will be 207 times 10 to the 10 to the 3 megapascals, and alpha will be 12 10 to the negative 6 per degree Celsius. And the last one, tungsten. That will be E is equals to 407 times 10 to the 3 megapascals, and alpha will be 407. And this will be 4.5 times 10 to the negative 6. So these are the ones, and I want you to tell me which ones are okay and which ones are not okay.
Yeah.
So is copper okay or not? How about copper?
Yeah, no, we didn't notice the right box.
I think the person.
Can I think so? Sorry.
I'll come back. Okay, so which is copper okay or not? Is copper okay? Yes. So what did you get for copper?
104.2.
Yes, copper is 112.2 megapascal. So copper is okay.
Yes.
You all agree with that? How about the brass?
116.
116.6 megapascal. So brass also okay. Steel,
It's not okay.
not okay. 148.8. Tungsten.
Okay.
Tungsten is okay, which is 109.8 megapascals. Any questions? Okay, so that's regarding the thermal stress. Previous question was thermal flux. This question is thermal stress. Now the next question.
But when would be the other way around?
What's that?
Like, if it's a higher stress, shouldn't it be higher than 125? No, no.
Okay. This much of stress is induced in the material. You have this much of stress, for example, for aluminium. And the maximum thermally induced tensile stress of 125 is possible. So this is the maximum possible stress. That part can't handle more than that stress. So your stress should be less than that. Otherwise, the supports will break. Yes, supports can hold that. So it's going to shrink, but supports are pulling. Supports can take only up to that much of 125.
Okay.
So for example, you just take something, a rubber band, and you are pulling it. There is a maximum the rubber band can handle. But here the supports, not like, it's happening in the supports. Supports can't hold it. Any other question? Okay, next question is on thermal expansion, the volume changes or the length changes. To what temperature must a cylindrical rod of tungsten? So we have a cylindrical rod of tungsten with a diameter of 10 millimeters. Diameter and a plate. So we have a plate. That plate, or maybe a plate, we can draw it in any way. So it's a plate and it has a hollow. And this one is 9.988 millimeter diameter. Have to be heated. So this is steel, and this is tungsten. And what we need to do is we need to heat both the materials in a way that we can put this one inside this. So when we heat up, for example, we need to increase the temperature to a certain value, TF. So at this particular temperature, TF, to rod to be, if you can put the rod inside that hollow part, what should that, like, what is the requirement? So the final diameter at this particular temperature, TF, the diameter here should be equal to the diameter here. Do you agree? If both the diameters are equal, then it fits, isn't it? So that's our requirement. So at a particular temperature, if both the diameters are equal, then we need to find that particular temperature, isn't it? So what do we know about thermal expansion? We know change in the length. Change in the length divided by the original length is equals to alpha times change in the temperature. Am I right? So length can be a diameter or a length, any linear length. So this will be our final diameter over the initial diameter divided by the initial diameter. It should be like this, isn't it? So our equation, we can write our equation in this way. Am I right? So here, if I further solve this one, I can say dF is equals to d naught plus d naught alpha delta t. Is this right or wrong? Can I make the dF the subject in that equation?
That's right.
So if you find the dF using this equation for both of these materials, in a particular temperature, we can find the delta T, which is responsible for having the same dF. Do you agree with that? So can you please write the two equations, one for tungsten and one for steel? What are the things changing? So when you're looking at the tungsten, these diameters are different because it is 10 millimeters. And also, this will be different because we are using tungsten. I'm going to give you thermal expansion coefficient will be different for tungsten and steel. But this will remain the same. Am I right? This doesn't change. We both are at 25 degrees Celsius. And when you heat up, both will be in your final temperature. So this delta T is the same for tungsten or steel. Only things changing is the initial diameter and the thermal expansion coefficient. Agree? Okay, so can you please write me the equations? So for tungsten, alpha is equals to, for tungsten, alpha is equals to 4.5. 4.5 times 10 to the negative 6 per degree Celsius. And for steel, alpha is equals to, it's 316 stainless steel. So it's a different one than the previous one, isn't it? So 16 times 10 to the negative 6. It's a different steel. So these two are known. Can you please write me the two equations, one for tungsten and one for the steel? You can't cool one material and you are not heating the other. When you cool this one, you make it smaller. This is cooling, how the cooling expands. When you heat up, it expands, except water.
And the material expands, what doesn't get smaller, because there's a hole in the middle, right? It makes these that's around the hole and hole gets smaller.
It depends. So it's not, you can't say that this is staying here, only if the reduction is happening like this. The whole thing will increase. It's the area expansion. This will become like this. Your square will expand. So your square will expand like this. And this will expand as well. You can't say it's the square is staying like, if you have restrictions, if you put something, there are barriers to not to expand it, yes, then the hole will get expanded. But if you don't have barriers that will expand, the whole thing will expand. That makes sense? So when we increase the temperature, what will happen? This will get bigger like this. And also this will get bigger. This will get expanded and this one also get expanded like that. That's why the hole is get enlarged as well because of that. Otherwise, if you keep restrictions from the four sides like this, if we have restrictions, yes, then the hole gets smaller because there are nowhere else to expand. So that material will go inside and it makes the hole smaller if we have restrictions. But here they don't say it has restrictions, so the whole thing will expand. So the hole also get expanded. Okay, so if I write the equation for dF here, I can write dF is equal. So you can keep in millimeters. Our answer also will be in millimeters. It's okay to keep millimeters. Okay, so alpha is 4.5 times 10 to the negative 6 times delta T here. And here, if you write it, it will be 9.98, 9.988 plus 9.988 times 16 times 10 to the negative 6 times delta T. Am I right? Is this what you wrote? So now you can equal these two. If you equal these two, what will happen? So then you have 10 plus 10 times 4.5 times 10 to the negative 6 delta T is equals to 9.988 plus 9.988 times 16 times 10 to the negative 6 times delta T. Is this right? Now you need to take delta T. Our aim is to find this delta T. If we find that delta T, I need to take this one to this side and this one to that side. Am I right? So we can have 10 minus 9.988 in this side. And here we have delta T is common. 10 to the negative 6 is common. We have 9.988 times 10, 988, sorry, minus times 16 minus 4.5 times 10. So this is what I got. Do you get the same? Is this right? So can you solve this and find me the delta T, please? I'm just rearranging the equation in a way that I can make delta T the subject. I need to find delta T. It's just maths, not materials. Yes, it should have. Yes, yes. See, this 10 is there. You see that? And this, like this one has. What do you get as delta T? Yes, so delta T is equals to, we get, here we get this one is 0.012. And that the other one will be, yeah, so you can put this in the calculator. So delta T is 104.5 degrees Celsius. So delta T is this. So what should be the final temperature? Initially is 25 degrees Celsius. Change in the temperature is 104.5. So what should be the final temperature? Yes, so final minus the initial will be this 104.5. So final will be 104.5 plus 25, which is 129.5 degrees Celsius. So if we heat both of these parts to 129.5 degrees Celsius, that tungsten rod will fit in the steel hollow. Am I right? Any question? So that will cover those three questions, will cover all three parts. One is heat flux. First question was on heat flux, heat transfer. The second question was on thermal stress, and this one is on thermal expansion. So have you seen the thermal expansion, the precautions for thermal expansion when you look around? Have you seen them? Have you seen the expansion joints in concrete, in footpaths, in your driveway? Do you see that at your place? And also, have you seen the railway trucks? Do you see that they have something? Otherwise, during the winter, they will contract, and during the summer, it will expand, and the trucks will sag otherwise if you don't provide that expansion allowance. And again, on roads also you see these expansions with metal plates going like this, place to place. In bridges, everywhere you see that. So we need to consider that depending on the material, that expansion will be different. So we need to do that things like, you know, whatever your field is, civil, mechanical, electrical, whatever it is, you need to learn this basic stuff. Are we good? Any question? No questions. So the question number 4 is my bonus question. So let's do this one, and then I'll show you the question number 4, which you have as the bonus question next week. So can you give me, yes?
Do we have to submit it next week or the week after? Because we have a
The week after, yes, week after. Okay, so this, what will be the answer for this one? Thermal expansion is the change in mass, volume, density, or heat capacity of a material. What is the definition of thermal expansion? Change in the volume. If we consider the linear direction, it will be change in the length, area-wise change in the area, volume-wise change in the volume. So the whole volume will change, but depending on what we are looking at, we can either consider it as linear, area, or volume. But the answer should be volume. Density also changes. Why the mass doesn't change? When you increase or decrease, mass doesn't change. But the density will change because density is the mass divided by the volume. So when the volume changes, the density changes, isn't it? And heat capacity is not the thermal expansion. Heat capacity is the ability of a material to transfer heat energy, heat. The next question, metals generally have higher thermal conductivity compared to ceramics, polymers, both ceramics and polymers, none of the above. Both. So you also see this in your cooking pans. The handle is a polymer most of the times, like we have something to, the pot is metal. And what else? Why the metals will transfer heat or electrical conductivity is higher in metals? Because if you look at the metallic bonds, we have an electron clouds and metal nucleus is staying there. So electrons can easily move, vibrate and move. So heat and also electricity, they or both can be like, metals are better in transferring or conducting them. So in some situations, we need to select something which insulators, thermal insulators, or else electrical insulator. In that case, polymers are better. Okay, so any question regarding this one? No questions. Okay, so this is the bonus question. Briefly explain why the thermal conductivity are higher for crystalline than for non-crystalline. So crystalline and non-crystalline. Crystalline means you have the repeating unit as a arranged way. Non-crystalline means they are randomly staying. So you have to read few slides in your lecture notes to understand this, and I want you to write a small paragraph. Are we good? Any question? So next week is your quiz.